Vectored instruction had its origins when I was studying physics.
Really?
And they taught us about vectors. And vectors in physics are very, very useful tools. Like you talked about forces. Mm-hmm. A force is a vector because a vector is something that has a magnitude, but it also has a direction. When you talk about forces, you got to think which direction is that force pushing in. So how strong is the force and which direction is it pushing? And so you get into vector analysis of forces. And I was enthralled by it. It's just, isn't it? This is neat physics stuff. We like this. Well, when we got into education, I realized that students go along and then all of a sudden they hit something and it's like a brick wall. They run into it, they can't get through, they get up, they run at it again, and finally they get sore and they give up. And they just can't get through. And I said, well, why can't they get through? And let's make a science of studying why these kids can't get through this particular concept. And it became very interesting. With millions of students on Acellus, we could get some pretty good data. And we started finding out, well, sometimes it's because they weren't interested. But more often, it was because they didn't have the right foreknowledge or requisite knowledge to be able to learn this particular topic. Lots of times it was as simple as vocabulary. The teachers were using words the kids didn't know. And they look at it like that and they're dead. Sometimes they were learning a concept that required 2 or 3 concepts before, so you know where to put them. And so I said, well, let's start studying these roadblocks in education. When a student is moving along, getting stuck in a classroom, they've got a teacher there. Come and help me, come and help me. When they're on a computer, they need to have something to help them when they get stuck. So we started developing, first of all, a tool called deficiency diagnostics. This is a tool that is triggered every time you get stuck. And I'm going to give you students that are using Acellus a little secret. When you're doing Acellus and you run into a roadblock, what should you do? A, slam down the computer, give up.
Did they get that option?
B, and it turns out that the right choice is you try and try and try. Because as soon as you get stuck, the Acellus engine, that's the program that runs Acellus, immediately detects we've got a problem. That person on the second row is stuck right here. And so all of these tools swing over and start watching to find out why she's stuck. And it starts analyzing, and you have to keep trying. If you quit trying, they don't have any data. But if you keep trying, then it starts saying, okay, she's struggling with this concept. She's struggling with that concept. And so then it starts figuring out what instruction could we give this student to break through this brick wall. And that would be the vectored instruction. And it's really pretty magical. The results have been truly magical. Mm-hmm. Let me give you a little bit of an example. How many of you like pie? In science, in math, pi is a thing that you've heard of, and we've heard some strange things about it, but most people don't know what pi is. You know, pie. Do you like pie? Yeah, it's cherry pie, exactly. Pi, we know, is a number that starts out 3.1, and then it keeps adding digits. And no matter how many digits you write down as part of the value of pi, you never run out of digits. There are pi books, literally books of pages and pages and pages of the digits after the decimal, and they just keep going and going and going, and it never comes out. Wow. It's a very, very unique and strange number, but most people don't know, well, what is it? What is the significance of it? I thought a good example to explain vectored instruction would be to serve pi. I would like it if everybody today could finish this episode of Science Live owning pi, knowing what pi, not apple pie, but mathematical pi, what it really is, what it signifies, where it came from, and why it's so doggone important. Okay?
Okay.
Some people say that pi is a magical number. It's a number that pops out of nature. And it's really, really interesting. So where do we get pi? I have used this pen to create some artwork, show people about pi. So here it is. Look at this. I have a circle, and the distance around this circle is the circumference. Now, I could get a ruler and measure it in inches, right? And the distance across this circle is the diameter. Most of us understand, if a circle's this big, then the diameter is the distance across at the widest point. Okay, radius is from the center out to the circle. Diameter is the distance all the way across. Circumference is the distance all the way around the circle. So now here comes the magic formula. Pi, which is this cute little symbol, some people call it double T, okay, but it's pi. It's equal to the circumference divided by the diameter. So if you measure the distance around the circle and divide it by the diameter, that simple ratio is pi by definition. And no matter how big your circle is, pi is always the same. It's a property of a circle. The ratio of the diameter to the distance around is always a little more than 3 times. It's 3 times around to what it would be straight across. So if you're hiking, you just want to go straight across. You wouldn't want to go clear around, would you? That ratio then becomes magical. And the fascinating thing, it's not one of those things where if the distance around is 3 and the cross is 1, then pi is 3, because the magic of this geometry is that it never comes out to be exactly just one number. When you divide, if you divide 5 into 10, the answer's 2. But if you divide 5 into 11, then it gets a little more complicated. Let's see if I can remember how to divide. 5 into 11. So 2 times 5 is 10. Yeah, and 5 into 10 is 2. So 5 will go in 11, 2.2 times. And look, it came out even, because 2 times 5 is 10, 0. But if you do this with this ratio, it never comes out even. There's always a remainder left over, as many times, even if you do it thousands and thousands and thousands of digits. And that makes it a very, very special kind of number. And some people say that there's some magic in that. And that's where they get into sacred geometry and all that stuff. Well, I think it's really interesting to understand that. And that leads us to things in engineering and science that we're able to create rocket ships. We're able to create bridges and things like that. Radians, not everybody that hasn't had very much math even knows what radians are. And e-exponentials and things of that sort. It's all coming out of this kind of stuff. And it's very, very wonderful and valuable. So pi is simply the ratio of the distance around a circle compared to the distance across. That's all it is. And yet we are able to do things with that that are simply magical. So if a person doesn't know what pi is and they get a problem based on pi and they don't have an understanding of it, they're stuck. And the only way they go forward is you change to another class, or you fill them in. You feed them a pie. You help them learn about it. So the idea of vectored instruction is to come in and help them fill in to where they can go forward. Now, vectored instruction is implemented widely in Acellus. And so when you run into a problem, you just keep doing your best, and the system adjusts. And you'll be surprised how it will help you get through it. And we watch the data on different students, and you run into an obstacle, a place where you can't get through, it is able to diagnose what things you're missing. It goes out and it gets instruction that isn't even part of this class. And it fills in the blanks for you. Maybe it was something that you were on vacation when they taught it in your last class or 3 years ago. It fills it in, and then all of a sudden you come back and we see you going forward again. It really, really, really is magical. And it's one of the reasons that the schools, the big schools that are using Acellus, are seeing such tremendous increase in outcomes. Graduation rates, standardized test scores going way up. And one of the big differences is students' attitudes are changing. If you as a student ever get to the point where you say, I'm stupid, you're not going to learn. You got to believe in yourself. And there is no better way to believe in yourself than having success. When you start having success and start moving forward, you know, wow, this isn't so hard. I can do this. Then your whole attitude changes. And Tobias was talking about, you know, what kind of a day is it? How good's the weather? Well, I'll tell you what, how good the day is depends an awful lot on how good you feel about yourself. Yeah. What kind of day? Oh, it's a great day. It's freezing. It's like I said, it's a great day. It changes everything.